What is the language of the universe? What is the hidden code? Imagine if I told you that these tiny grains of sand are following the exact same code as the spiral galaxies spinning billions of light years away. Sounds crazy, right? But here's something even wilder. The mathematics hiding behind everything you're seeing right now, this screen, your hands, even the thoughts firing in your brain, all follow patterns so precise that some of the world's leading scientists are starting to wonder if we're living in some kind of cosmic computer program. In the next 15 minutes, I'm going to show you 3 mind-bending secrets about the universe that will completely change how you see, well, everything. We'll dive into quantum physics, dark matter, and something so strange that Einstein called it spooky action at a distance. But first, let me show you something that's going to blow your mind. You see this simple flower? It's actually hiding a mathematical code that appears everywhere, from the spiral of hurricanes to the shape of entire galaxies. And once you see it, you'll never look at the world the same way again. But before we dive into these forces, there's something strange you need to know. Scientists recently discovered that about 96% of our universe is missing. Not just hidden, missing. And what's even more bizarre is that this mystery is connected to that flower pattern I just showed you. Let me explain. At the heart of the universe are the 4 fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. These forces are the building blocks of all interactions in nature, from the movement of planets to the behavior of atoms. Gravity, the most familiar of the forces, is responsible for the attraction between masses. It governs the orbits of planets around stars, the motion of galaxies, and even the shape of the universe itself. However, gravity is by far the weakest of the 4 forces, though it operates over vast distances and affects massive objects. Electromagnetism governs the behavior of charged particles and is responsible for light, electricity, and magnetism. It plays a crucial role in the formation of atoms and molecules, and its influence is felt on both the smallest and largest scales of the universe. The strong nuclear force holds the nuclei of atoms together, overcoming the electromagnetic repulsion between protons. Without this force, atoms could not exist, and the universe would be a vastly different place. Finally, the weak nuclear force is responsible for processes like nuclear decay, which allows for the transformation of one element into another. This force plays a critical role in the life cycles of stars, particularly in the process of fusion that powers them. Together, these forces form the fundamental framework of the universe. Their precise balance and interaction are essential for the formation of matter and the development of complex structures like galaxies, stars, planets, and life itself. The question that arises is, why are these forces so perfectly tuned? This brings us to the idea of the fine-tuning of the universe. Is the fine-tuning of the universe a cosmic coincidence or a hidden code? One of the most remarkable aspects of the universe is that the constants governing these forces appear to be finely tuned in such a way that they allow for the existence of life. This is known as the fine-tuning problem. If any of these constants were even slightly different, the universe as we know it would not exist. For example, if the strength of the strong nuclear force were just a little weaker, atomic nuclei would not hold together, and complex elements like carbon and oxygen, essential for life, would not form. If gravity were slightly stronger or weaker, stars would not have stable life cycles, preventing the formation of planets capable of supporting life. The fine-tuning of these constants has led some scientists and philosophers to propose that the universe is governed by an underlying code, a set of mathematical rules and principles that dictate its behavior. But this raises profound questions. Why is the universe so finely tuned? Is it the result of chance? Or is there a deeper reason behind the seemingly perfect balance of these forces? Some argue that this fine-tuning suggests the existence of a multiverse, a vast ensemble of universes, each with its own set of physical laws and constants. In this view, our universe just happens to be one in which the conditions are right for life. Others propose that the fine-tuning is evidence of a deeper, hidden structure to reality. a code embedded in the fabric of the universe itself. If the universe operates according to a hidden code, then mathematics is the language in which that code is written. Throughout history, scientists have discovered that the laws of nature can be described with stunning precision through mathematical equations. From Newton's laws of motion to Einstein's theory of general relativity, mathematics provides a framework for understanding the universe. Consider Euler's identity, often described as the most beautiful equation in mathematics. It combines 5 of the most important mathematical constants: the exponent e, the imaginary number I, the ratio of the circumference of any circle to its diameter pi, unity, which means the number 1, and 0, the number representing nothingness. In a single elegant expression, exponent to the power of the product of the imaginary number and pi plus 1 equals 0. This equation, which links seemingly unrelated branches of mathematics, hints at a deep underlying unity in the structure of reality. Mathematics doesn't just describe physical phenomena, it also predicts new discoveries. For instance, the planet Neptune was discovered in the 19th century not through direct observation, but by applying Newton's laws of gravity to the motion of Uranus. Similarly, the existence of antimatter was predicted by Paul Dirac's equations before it was ever detected in experiments. This predictive power suggests that mathematics is not just a human invention, but a fundamental aspect of the universe itself, a hidden code that governs the behavior of matter, energy, and space-time. But what is the nature of this code? Is it deterministic, meaning that the future of the universe is already written? Or is there room for randomness and unpredictability? At first glance, the universe appears to operate with perfect order. The motion of planets follows predictable paths, the behavior of particles can be described by precise equations, and the laws of physics seem unchanging. Yet, within this apparent order, there is also chaos. Chaos theory, which studies systems that are highly sensitive to initial conditions, shows that even in deterministic systems, small variations can lead to unpredictable outcomes. One of the most famous examples of chaos theory is the butterfly effect, the idea that the flap of a butterfly's wings in one part of the world could set off a chain of events leading to a hurricane in another. In the universe, chaotic systems can be found everywhere, from the behavior of weather patterns to the dynamics of galaxies. But even within chaos, there is underlying order. Fractals, for instance, are mathematical patterns that repeat at different scales, creating intricate self-similar structures. Fractals appear throughout nature, in the branching of trees, the shapes of coastlines, and the distribution of galaxies in the universe. They represent a kind of hidden order within seemingly chaotic systems. This dual nature of the universe, the interplay between chaos and order, raises profound questions about the hidden code of existence. Is the universe deterministic, with every event unfolding according to a fixed set of rules? Or is there an element of randomness, allowing for creativity and novelty in the unfolding of the cosmos? Another fundamental aspect of the universe's hidden code is symmetry. Symmetry refers to the idea that certain properties of a system remain unchanged under specific transformations, such as rotations, reflections, or translations. In physics, symmetries play a crucial role in defining the laws of nature. For example, the laws of conservation, including the conservation of energy, momentum, and angular momentum, are all tied to symmetries in the laws of physics. Noether's theorem, developed by mathematician Emmy Noether in 1915, showed that every conservation law corresponds to a symmetry in nature. For instance, the conservation of energy is related to the fact that the laws of physics do not change over time. Symmetry also plays a central role in particle physics. The Standard Model, which describes the fundamental particles and forces of the universe, is based on a set of symmetries that govern the interactions between particles. These symmetries help explain why particles behave the way they do, and why certain processes are allowed while others are forbidden. Yet, the universe is not perfectly symmetrical. One of the great mysteries of cosmology is the asymmetry between matter and antimatter. According to the laws of physics, The Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated each other, leaving behind nothing but radiation. However, for reasons that are not fully understood, there was a slight excess of matter, which allowed the universe to form. This asymmetry is a crucial part of the hidden code of existence, and understanding it could unlock new insights into the fundamental nature of reality. At the smallest scales, the universe operates according to the principles of quantum mechanics, a branch of physics that describes the behavior of particles at the atomic and subatomic levels. Quantum mechanics reveals a world that is fundamentally different from the one we experience in our everyday lives. A world where particles can exist in multiple states at once, where probabilities govern outcomes, and where the act of observation can influence reality. One of the key features of quantum mechanics is the concept of superposition, which allows particles to exist in a combination of multiple states simultaneously. This idea is famously illustrated by Schrödinger's cat, a thought experiment in which a cat in a box is both alive and dead until it is observed. Another crucial aspect of quantum mechanics is entanglement, in which particles become linked in such a way that the state of one particle is instantly correlated with the state of another, regardless of the distance between them. This spooky action at a distance, as Einstein called it, challenges our classical understanding of space and time, and suggests that the universe is interconnected in ways that we are only beginning to understand. Quantum mechanics operates according to a mathematical framework known as quantum field theory, which describes how particles interact with each other and with fields like the electromagnetic field. Quantum field theory provides the most accurate description of the universe at the smallest scales, and its equations are part of the hidden code that governs the behavior of particles. But quantum mechanics also introduces an element of randomness into the universe. Unlike classical physics, where the future can be predicted with certainty based on initial conditions, quantum mechanics only provides probabilities for different outcomes. This raises a fundamental question. Is the universe deterministic, or is it governed by randomness at the most fundamental level? What if we could access the hidden code? Imagine for a moment that you had access to the hidden code of the universe, the mathematical principles and equations that govern everything from the motion of galaxies to the behavior of subatomic particles. With this knowledge, you could predict the future with perfect accuracy, knowing the outcome of every event before it happens. You could understand the deepest mysteries of the cosmos, from the nature of dark matter and dark energy to the origin of the universe itself. But having access to the hidden code also raises ethical and philosophical questions. If the universe is deterministic and everything is governed by a fixed set of rules, does that leave any room for free will? Are we simply following a pre-written script, or do we have the ability to shape our own destinies? This thought experiment highlights the profound implications of the hidden code of existence. It challenges us to consider the nature of reality, the limits of human knowledge, and our place in the cosmos. The quest to unlock the hidden code of the universe is one of the most ambitious and enduring endeavors in science and philosophy. From the fundamental forces and the fine-tuning of physical constants to the mysteries of quantum mechanics and chaos theory, the universe is filled with clues that hint at a deeper underlying structure. As we continue to explore the cosmos, we are constantly uncovering new layers of complexity and order, revealing a universe that operates with a precision and elegance that is nothing short of awe-inspiring. While we may never fully decode the ultimate nature of reality, the journey itself is a testament to the power of human curiosity and the infinite possibilities that await us in the universe. Let's start by exploring cosmic codes in nature, the patterns of existence. In our journey to understand the hidden code of the universe, we've explored the fundamental forces and fine-tuning that govern the cosmos. But this code doesn't just exist in the abstract realm of mathematics and physics. It reveals itself in the patterns and structures we observe in nature. From the spiral arms of galaxies to the fractal shapes of coastlines, the universe is filled with repeating forms, symmetries, and geometries that hint at a deeper order. In this chapter, we'll explore some of the most remarkable natural patterns that embody the hidden code of existence. We'll look at the mathematical principles behind these patterns, from the Fibonacci sequence to the golden ratio, and discuss how they appear throughout the universe, linking everything from the smallest scales of life to the largest structures in the cosmos. One of the most famous patterns found in nature is the Fibonacci sequence, a series of numbers where each number is the sum of the two preceding ones: 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. This sequence appears in a wide variety of natural phenomena, from the arrangement of leaves on a stem to the spiral patterns of shells and galaxies. The Fibonacci sequence is more than just a numerical curiosity. It's a fundamental aspect of the way nature organizes itself. For instance, many plants grow leaves in a spiral pattern that follows the Fibonacci sequence, allowing for the most efficient use of sunlight. Similarly, the number of petals on many flowers corresponds to a Fibonacci number, as does the arrangement of seeds in a sunflower's head. But why does this sequence appear so frequently in nature? The answer lies in its connection to the golden ratio, a mathematical constant approximately equal to 1.618. As the Fibonacci sequence progresses, the ratio of consecutive numbers in the sequence approaches the golden ratio. This ratio has been found to represent the most efficient way to organize space, which is why it appears so often in biological structures that have evolved to optimize their growth and survival. The golden ratio doesn't just appear in nature. It has been used by humans for millennia in art, architecture, and design. From the proportions of ancient Greek temples to the works of Leonardo da Vinci, the golden ratio has long been recognized as a symbol of beauty and harmony. But its presence in nature suggests that it is more than just an aesthetic principle. It may be a fundamental aspect of the universe's hidden code. While the Fibonacci sequence and the golden ratio reveal the beauty of mathematical relationships in nature, fractals showcase the universe's ability to generate infinite complexity from simple rules. A fractal is a geometric pattern that repeats at different scales, creating intricate structures that are self-similar across various levels of magnification. One of the most famous examples of a fractal is the Mandelbrot set, a mathematical set of points that produces a stunningly intricate pattern when graphed. As you zoom in on the Mandelbrot set, you discover smaller and smaller versions of the same pattern, continuing infinitely. This self-similarity is a hallmark of fractals and can be found in many natural phenomena. Fractals appear in the branching patterns of trees, the structure of river networks, the shape of clouds, and even in the formation of mountain ranges. The coastlines of continents also exhibit fractal properties, with their jagged edges displaying the same level of complexity whether viewed from space or up close. In biology, fractals can be seen in the structure of lungs, blood vessels, and the intricate designs of snowflakes. But fractals are more than just visually striking patterns. They represent a deep connection between simplicity and complexity, showing how the universe can generate vast diversity and intricate detail from a few basic rules. In this way, fractals are a reflection of the hidden code of the universe, embodying the interplay between chaos and order. Another recurring pattern in nature and the cosmos is the spiral, a form that can be seen in everything from galaxies to seashells to hurricanes. Spirals are one of the most common shapes in the universe, and their ubiquity hints at a fundamental aspect of how nature organizes itself. In mathematics, spirals can be described by simple equations that involve growth and rotation. One of the most famous spirals is the logarithmic spiral, also known as the golden spiral because its growth factor is related to the golden ratio. This type of spiral appears in many natural systems, such as the shells of nautilus and ammonite fossils, the arrangement of seeds in sunflowers, and the arms of spiral galaxies like the Milky Way. The reason spirals appear so frequently in nature has to do with the efficiency of this shape in growth and distribution. For example, in a sunflower, the seeds are arranged in a spiral pattern to maximize the number of seeds that can fit in the flower's head, ensuring that no space is wasted. Similarly, spiral galaxies are shaped by the rotation and gravitational forces of their stars, forming an elegant and stable structure. Spirals also appear in the motion of fluids, such as the swirling patterns of hurricanes and whirlpools. These spirals arise from the way energy and matter move in response to forces like gravity and pressure, revealing the dynamic nature of the universe's hidden code. When we think of natural structures, the hexagon is not usually the first shape that comes to mind, but it is one of the most efficient and stable patterns in nature. Hexagons are a common feature in the natural world, from the honeycombs built by bees to the crystal structure of snowflakes. The reason hexagons are so prevalent in nature is that they are the most efficient way to cover a surface without leaving gaps. In a honeycomb, for example, hexagonal cells allow bees to store the maximum amount of honey using the least amount of wax. This efficiency is crucial for survival, as it minimizes the energy bees need to expend in building their nests. Hexagons also appear in the arrangement of molecules in certain crystals, such as quartz and ice. In snowflakes, the molecular structure of water causes the formation of hexagonal crystals, giving rise to the beautiful, symmetrical patterns that we see in snowflakes. But hexagons aren't limited to small-scale structures. On a much larger scale, the planet Saturn has a massive hexagonal storm at its north pole, a feature that has puzzled scientists since its discovery. The formation of this giant hexagon is thought to be related to the dynamics of fluid motion and atmospheric conditions on Saturn, but its precise origin remains a mystery. Hexagons, like spirals and fractals, represent the universe's ability to generate complex and efficient structures from simple rules. Whether in the microscopic world of crystals or the vastness of planetary atmospheres, hexagons reflect the hidden code that governs the organization of matter and energy. While symmetry is a key feature of the universe's hidden code, the process of symmetry breaking is equally important in understanding the evolution of the cosmos. Symmetry breaking occurs when a system that starts in a perfectly balanced state shifts into a new, less symmetrical state. This process is responsible for some of the most fundamental aspects of the universe, from the formation of galaxies to the creation of the elements. In the early moments after the Big Bang, the universe was in a state of near-perfect symmetry, with all the fundamental forces and particles unified. However, as the universe expanded and cooled, this symmetry broke, leading to the separation of the fundamental forces and the formation of distinct particles. This process is known as spontaneous symmetry breaking, and it is responsible for the universe's current structure. One of the most important examples of symmetry breaking in physics is the Higgs mechanism, which explains how particles acquire mass. In the early universe, particles were massless, but as the universe cooled, the Higgs field underwent symmetry breaking, giving rise to the masses of particles like protons, neutrons, and electrons. Symmetry breaking is also a key concept in the formation of galaxies. After the Big Bang, the universe was nearly uniform, but small fluctuations in the density of matter caused regions to collapse under gravity, forming galaxies, stars, and planets. These fluctuations broke the initial symmetry of the universe, allowing complex structures to emerge from the seemingly chaotic early universe. Imagine standing at the edge of the universe, watching as the hidden code of existence unfolds before your eyes. As you gaze into the vastness of space, you begin to notice patterns emerging from the cosmic backdrop, spirals in the arms of galaxies, hexagons in the structure of distant worlds, and fractal shapes in the distribution of matter. You see how these patterns repeat at different scales, from the smallest particles to the largest cosmic structures. Each pattern is a reflection of the underlying rules that govern the universe, a glimpse into the hidden code that shapes reality. But as you watch, you also notice moments of chaos and randomness. The way galaxies collide and merge, the unpredictable paths of stars, and the turbulent motion of fluids in space. Yet, even in this chaos, there is a deeper order, a symmetry that guides the unfolding of the universe. This thought experiment reminds us that the universe is both predictable and unpredictable, ordered and chaotic, simple and complex. It challenges us to look deeper into the patterns of existence and to uncover the code that lies at the heart of reality. The patterns we observe in nature, from spirals and fractals to hexagons and symmetry breaking, offer us a window into the hidden code of the universe. These patterns reveal the deep mathematical structure that underlies the cosmos, showing how simple rules can generate infinite complexity and order. As we continue to explore the universe, we find that these patterns are not just aesthetic curiosities, but are fundamental to the way the universe operates. They are the signature of the hidden code, the language of existence that governs everything from the growth of plants to the motion of galaxies. The study of these patterns is not just a journey into the natural world, but also a journey into the very nature of reality. It invites us to question how the universe is organized, why certain patterns recur, and whether there is a deeper underlying order to the cosmos. In the next chapter, we will continue to unravel the mysteries of this hidden code by exploring the quantum realm, where the rules of reality become even more strange and counterintuitive. We will delve into the world of particles, fields, and probabilities, and uncover how quantum mechanics shapes the very fabric of existence. The quantum realm, decoding reality at the smallest scales. As we continue to unlock the hidden code of the universe, we now shift our focus to the realm where reality behaves in the most unexpected ways: the quantum world. Quantum mechanics, the branch of physics that governs the behavior of particles at the atomic and subatomic levels, introduces us to phenomena that challenge our intuitive understanding of the universe. This realm reveals a world of uncertainty, probability, and interconnectedness, a world that is key to understanding the very fabric of existence. In this chapter, we'll explore how quantum mechanics uncovers the hidden code at the smallest scales, from the peculiar behavior of particles to the nature of quantum fields. We'll delve into thought experiments like Schrödinger's cat, discover the role of quantum entanglement, and investigate how this strange world may hold the key to answering some of the universe's most profound mysteries. One of the cornerstones of quantum mechanics is Heisenberg's uncertainty principle, a fundamental concept that sets limits on how precisely we can know certain properties of a particle, such as its position and momentum, at the same time. According to this principle, the more accurately we know a particle's position, the less accurately we can know its momentum, and vice versa. This is not simply a matter of measurement difficulty. It is a reflection of the underlying nature of reality in the quantum realm. In classical mechanics, we assume that objects have definite properties that we can measure with increasing precision. But in the quantum world, particles do not have fixed positions or momenta until they are observed. Instead, they exist in a superposition of all possible states, only choosing a particular state when measured. This uncertainty is an intrinsic part of the hidden code of the quantum world. It tells us that the universe, at its most fundamental level, is probabilistic, not deterministic. This means that even if we had perfect knowledge of a quantum system, we could never predict its behavior with absolute certainty. We can only calculate probabilities. The uncertainty principle has profound implications for our understanding of reality. It challenges the classical notion of a clockwork universe, where every event is determined by the initial conditions of the system. Instead, the quantum world introduces an element of randomness and unpredictability, suggesting that the universe's hidden code allows for creativity and spontaneity at the smallest scales. In the quantum realm, particles can exist in multiple states simultaneously, a phenomenon known as superposition. This concept is famously illustrated by Schrödinger's cat, a thought experiment devised by physicist Erwin Schrödinger to highlight the strange implications of quantum mechanics. In this experiment, a cat is placed in a box with a vial of poison that is released based on the state of a quantum particle. According to quantum mechanics, until the box is opened and the system is observed, the particle exists in a superposition of states, both releasing the poison and not releasing it. As a result, the cat is both alive and dead at the same time, a paradox that highlights the bizarre nature of superposition. While Schrödinger's cat is a hypothetical scenario, it illustrates a fundamental truth about quantum mechanics. Particles can occupy multiple states until they are observed. This raises questions about the nature of reality. Does the act of observation collapse the superposition, choosing one outcome over another? Or does the universe split into multiple branches, with each possible outcome occurring in a different branch of the multiverse? Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that every possible outcome of a quantum event actually occurs, but in separate parallel universes. In this view, the hidden code of the universe includes an infinite number of possibilities, each of which plays out in its own version of reality. This raises the tantalizing possibility that there may be countless versions of ourselves, living out different lives in parallel universes. Another deeply mysterious aspect of quantum mechanics is quantum entanglement, a phenomenon in which two or more particles become linked in such a way that the state of one particle is instantly correlated with the state of the other, no matter how far apart they are. This spooky action at a distance, as Albert Einstein famously described it, defies classical notions of locality and suggests that the universe is interconnected in ways we are only beginning to understand. When particles become entangled, their properties are no longer independent. They must be described as part of a single unified system. For example, if two particles are entangled and one particle is measured to have a specific spin, the other particle's spin will be instantly determined, even if the particles are light years apart. This instantaneous correlation appears to violate the speed of light limit set by special relativity, but it does not involve any information being transmitted between the particles. They are simply part of the same quantum system. Entanglement plays a crucial role in the hidden code of the quantum world, and its implications are far-reaching. It suggests that the universe is not composed of isolated independent objects, but rather of interconnected systems that are deeply linked, regardless of distance. This interconnectedness could provide insights into the fundamental nature of reality, hinting at a deeper level of order and structure that underlies the universe. Entanglement is also a key component of quantum computing, a revolutionary technology that leverages the principles of quantum mechanics to perform calculations far beyond the capabilities of classical computers. By harnessing the power of superposition and entanglement, quantum computers have the potential to solve complex problems in physics, cryptography, and artificial intelligence, unlocking new aspects of the universe's hidden code. One of the most perplexing aspects of quantum mechanics is the concept of wave-particle duality, which reveals that particles can behave both as particles and as waves, depending on how they are observed. This dual nature is most famously demonstrated in the double-slit experiment, a classic quantum mechanics experiment that challenges our understanding of the behavior of particles. In this experiment, particles such as electrons are fired at a barrier with two slits, and a detector on the other side records where they land. When both slits are open, the particles produce an interference pattern on the detector, as though they were behaving like waves, passing through both slits simultaneously and interfering with themselves. However, if a detector is placed at the slits to observe which slit each particle passes through, the interference pattern disappears, and the particles behave like classical particles, passing through only one slit. This experiment highlights the fundamental mystery of wave-particle duality. Particles exist as waves of probability, capable of being in multiple places at once. But when observed, they collapse into a single, definite state. This duality is a key feature of the hidden code of the universe, revealing that reality is not as fixed and deterministic as it may appear. Wave-particle duality also has profound implications for the nature of reality itself. It suggests that objects do not have definite properties until they are observed, and that the act of observation plays a crucial role in determining the outcome of quantum events. This raises questions about the role of consciousness in shaping reality, as well as the nature of time and causality in the quantum world. At the heart of quantum mechanics is the concept of quantum fields, which describe the behavior of particles not as individual objects, but as excitations or disturbances in underlying fields. In this view, particles are not tiny, solid objects, but rather ripples in a quantum field that permeates all of space. For example, the electron is not a standalone particle, but an excitation in the electron field, which exists everywhere in the universe. Similarly, photons are excitations in the electromagnetic field, and quarks are excitations in the quark field. This field-based view of reality is described by quantum field theory, QFT, one of the most successful and accurate theories in modern physics. Quantum field theory provides a framework for understanding how particles interact with each other and with forces like electromagnetism and the strong and weak nuclear forces. It also forms the basis of the Standard Model of particle physics, which describes the fundamental particles and forces that make up the universe. But quantum field theory also introduces a new layer of complexity to the hidden code of the universe. According to QFT, empty space is not truly empty. It is filled with fluctuating quantum fields, constantly generating and annihilating virtual particles. These quantum fluctuations are believed to play a role in phenomena such as the cosmological constant, related to dark energy, and the vacuum energy of space itself. Quantum fields suggest that reality is far more dynamic and interconnected than classical physics would have us believe. They reveal a universe in constant flux, with particles and forces arising from underlying fields that stretch across all of space and time. Imagine that you could shrink yourself down to the size of a subatomic particle and enter the quantum realm. As you navigate this strange, fluctuating landscape, you encounter particles that flicker in and out of existence, wave-like ripples that stretch across space, and entangled particles that communicate instantly across vast distances. You witness particles in superposition, existing in multiple states at once, and observe how the act of measurement collapses these possibilities into a single outcome. You see the interconnectedness of the quantum world, where even particles separated by vast distances are linked through entanglement. As you explore this realm, you realize that the universe's hidden code is not just a set of deterministic rules, but a probabilistic framework that allows for uncertainty, randomness, and creativity. This code shapes the very fabric of reality, guiding the behavior of particles, fields, and forces at the smallest scales. This thought experiment highlights the profound implications of quantum mechanics for our understanding of reality. It challenges us to think beyond classical notions of particles and forces and to embrace the strange, counterintuitive nature of the quantum world. Quantum mechanics reveals a universe that is both deeply mysterious and incredibly precise. From the uncertainty principle and wave-particle duality to quantum entanglement and fields, the quantum realm is governed by a hidden code that challenges our classical understanding of reality. This code operates at the smallest scales, yet it has far-reaching implications for the entire universe. It shapes the behavior of matter and energy, the structure of space and time, and even the nature of consciousness and observation. As we continue to explore the quantum world, we are uncovering new layers of the hidden code that governs the universe. This journey is far from over, and with each discovery, we gain a deeper understanding of the fundamental nature of reality, a reality that is far stranger and more complex than we ever imagined. In the next chapter, we will explore how this quantum code intersects with the forces of nature and the large-scale structures of the universe, revealing new insights into the hidden code of existence. The forces of nature, unlocking the power behind the universe's structure. Now that we've explored the quantum code that governs the smallest scales of reality, it's time to zoom out and examine how this hidden code manifests in the forces that shape the universe on larger scales. The universe as we know it exists because of four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Each of these forces operates according to precise rules, and together they form the foundation of the universe's structure, guiding the behavior of everything from the motion of galaxies to the fusion of elements within stars. In this chapter, we'll delve deep into each of these forces, uncovering their origins, roles, and interactions within the cosmos. We'll also explore the unification of forces, the idea that these seemingly distinct forces may be different expressions of a single underlying force. This exploration will help us decode another aspect of the hidden code of the universe: how these fundamental forces combine to create the complex and orderly universe we observe today. Gravity is perhaps the most familiar force to us, yet it remains one of the most mysterious. First described mathematically by Isaac Newton in the 17th century, Gravity is the force that attracts objects with mass toward one another. From the motion of planets around stars to the orbits of galaxies within galaxy clusters, gravity shapes the large-scale structure of the universe. But Newton's understanding of gravity was incomplete. In the early 20th century, Albert Einstein revolutionized our understanding of gravity with his theory of general relativity, which revealed that gravity is not a force in the traditional sense, but rather a warping of space and time caused by mass and energy. According to this theory, massive objects like stars and planets cause the fabric of space-time to curve, and this curvature is what we perceive as gravity. One of the most mind-bending predictions of general relativity is the existence of black holes, regions of space where gravity is so intense that not even light can escape. Black holes form when massive stars collapse under their own gravity at the end of their life cycles, and they serve as extreme examples of the warping of space-time. The hidden code of gravity is intricately linked to the geometry of the universe. Einstein's equations describe how matter and energy shape space-time, and in turn, how the curvature of space-time influences the motion of matter and energy. This feedback loop creates the dynamic and evolving cosmos we observe, where galaxies cluster, stars form, and black holes warp the very fabric of reality. But gravity also presents one of the greatest mysteries in physics. How does it fit into the quantum world? While general relativity describes gravity on large scales, it doesn't mesh well with the laws of quantum mechanics, which govern the behavior of particles on small scales. The search for a quantum theory of gravity, a theory that unifies gravity with the other fundamental forces, remains one of the greatest challenges in physics. While gravity governs the large-scale structure of the universe, electromagnetism rules much of the small-scale world. Electromagnetism is the force that acts between charged particles, and it is responsible for electricity, magnetism, and light. It governs the behavior of atoms, the formation of molecules, and the transmission of information across the universe via electromagnetic radiation. Electromagnetism was first described in the 19th century by James Clerk Maxwell, who unified the electric and magnetic forces into a single theory known as Maxwell's equations. These equations describe how electric and magnetic fields interact and how they give rise to electromagnetic waves, including visible light, radio waves, X-rays, and gamma rays. At the heart of electromagnetism is the photon, the quantum particle of light. Photons are massless particles that carry the electromagnetic force between charged particles, mediating interactions at both the atomic and macroscopic levels. Unlike gravity, which can only attract, electromagnetism can both attract and repel, depending on the charges involved. This allows for the wide variety of interactions that govern chemical reactions, the behavior of materials, and the transmission of light across the cosmos. The hidden code of electromagnetism is deeply connected to the structure of matter itself. Electromagnetic forces hold atoms together, allow for the formation of molecules, and enable the complex chemistry that is the foundation of life. Without electromagnetism, there would be no light, no communication between atoms, and no way for the energy of the sun to reach the Earth. Electromagnetism is also a key player in some of the most powerful cosmic phenomena. In pulsars, rapidly rotating neutron stars, the intense magnetic fields generated by the star's rotation create beams of electromagnetic radiation that sweep across space, acting like cosmic lighthouses. In supernovae, electromagnetic forces help accelerate charged particles to nearly the speed of light, creating cosmic rays that bombard the Earth. While gravity and electromagnetism shape the cosmos on large scales, the strong nuclear force operates at the heart of atoms, holding the fundamental building blocks of matter together. The strong force is the force that binds protons and neutrons in the atomic nucleus, overcoming the repulsive electromagnetic force between positively charged protons. The strong nuclear force is the most powerful of the four fundamental forces, but it only operates over incredibly short distances, on the order of a femtometer, 1/4,000,000th of a meter. Despite its short range, the strong force is absolutely essential for the stability of matter. Without it, atomic nuclei would fly apart, and the universe as we know it would not exist. The strong force is mediated by particles called gluons, which act as the glue that holds protons and neutrons together in the nucleus. Gluons carry the strong force between quarks, the fundamental particles that make up protons and neutrons. The interaction between quarks and gluons is described by quantum chromodynamics, QCD, a theory that is part of the standard model of particle physics. The strong nuclear force plays a crucial role in the energy processes that power stars. In the cores of stars like the Sun, the strong force enables nuclear fusion, the process by which hydrogen atoms fuse to form helium, releasing vast amounts of energy in the form of light and heat. This fusion process is what sustains stars throughout most of their lifetimes, providing the energy that supports life on Earth. But the strong force is also responsible for some of the universe's most violent events. When massive stars exhaust their nuclear fuel, the strong force can no longer hold the star's core together, leading to a supernova explosion. These explosions scatter heavy elements into space, seeding the cosmos with the building blocks for planets, moons, and life. The weak nuclear force may be the least familiar of the four fundamental forces, but it is no less important. The weak force is responsible for nuclear decay, a process in which subatomic particles transform into other particles. This force governs phenomena like beta decay, in which a neutron decays into a proton, an electron, and a neutrino. The weak force operates over extremely short distances, much like the strong force, but its effects are crucial for the evolution of the universe. For example, the weak force plays a key role in the fusion reactions that power stars, allowing protons to transform into neutrons during the process of creating heavier elements. Without the weak force, stars would not be able to fuse hydrogen into helium, and the universe would lack many of the elements essential for life. The weak force is also intimately connected to the Higgs mechanism, which gives particles their mass. In the standard model, particles interact with the Higgs field, acquiring mass through their interactions with the Higgs boson. This process is a form of spontaneous symmetry breaking, a key feature of the universe's hidden code, which allows for the diversity of particles and forces we observe today. The weak force's ability to change one type of particle into another makes it a transformative force in the universe. It allows for the gradual change of elements over time, contributing to the cosmic alchemy that has shaped the universe's evolution since the Big Bang. While each of the four fundamental forces governs different aspects of the universe, physicists have long sought a way to unify these forces under a single theoretical framework. This quest for a theory of everything aims to explain how the forces of nature are different manifestations of the same underlying principles. In the early universe, shortly after the Big Bang, it is believed that all the fundamental forces were unified into a single force. As the universe expanded and cooled, these forces began to break into the distinct forces we observe today. The first breakthrough in unifying the forces came in the 19th century, with Maxwell's unification of electromagnetism, which showed that electricity and magnetism were different aspects of the same force. In the 20th century, physicists made further progress by unifying the electromagnetic force and the weak nuclear force into the electroweak force. This unification was a key step in the development of the standard model of particle physics, which describes three of the four fundamental forces, excluding gravity. The next goal in this unification is the development of a grand unified theory, GUT, which would bring together the strong nuclear force with the electroweak force. Beyond that, physicists hope to one day develop a theory of everything that includes gravity, uniting all four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, under a single theoretical framework. This search for unification has led to some of the most exciting and challenging areas of modern physics, such as string theory and loop quantum gravity. These theories attempt to reconcile general relativity, which describes gravity on large scales, with quantum mechanics, which governs the behavior of particles at the smallest scales. While string theory proposes that all particles are made of tiny, vibrating strings of energy, loop quantum gravity suggests that space-time itself is composed of discrete loops, at the quantum level. Unifying the forces of nature would not only provide a deeper understanding of the universe's hidden code, but could also reveal new insights into the fundamental nature of space, time, and matter. It could help answer some of the most profound questions in cosmology, such as the true nature of black holes, the origin of the universe, and the fate of the cosmos. While each of the four fundamental forces operates in different realms, the universe we observe today is the result of their complex interplay. Gravity shapes the large-scale structure of the cosmos, pulling galaxies into clusters and stars into planetary systems. Electromagnetism governs the behavior of matter on smaller scales, from the formation of atoms to the light we see from distant stars. The strong nuclear force holds atomic nuclei together, enabling the fusion processes that power stars, while the weak nuclear force drives the nuclear reactions that create the elements necessary for life. The balance between these forces is delicate, yet it is what allows the universe to exist in its current form. For example, if the strong nuclear force were slightly weaker, atomic nuclei would not hold together, and complex elements like carbon and oxygen would not exist. If gravity were slightly stronger, stars would burn through their fuel too quickly, preventing the formation of planets and life. This fine-tuning of the forces suggests that the universe operates according to a hidden code, one that is perfectly calibrated to allow for the complexity and diversity of the cosmos. It also raises profound philosophical questions about the nature of reality. Is the universe fine-tuned by chance, or is there a deeper reason for the precise balance of these forces? Could this hidden code point to a multiverse, where different universes exist with different laws of physics, and we just happen to live in one where the conditions are right for life? Imagine for a moment that one of the four fundamental forces were suddenly turned off. What would happen to the universe? If gravity were to disappear, the effects would be catastrophic. Planets would no longer orbit stars, galaxies would disintegrate, and the large-scale structure of the universe would collapse. Without gravity, the universe would become a chaotic expanse of unbound matter, with no way to form stars, planets, or life. If electromagnetism were to vanish, the consequences would be equally dramatic. Atoms would cease to exist, as there would be no force to bind electrons to nuclei. Light would no longer travel through space, and chemical reactions would become impossible. Life, as we know it, depends on electromagnetic interactions, from the chemistry of DNA to the energy produced by the sun. Without the strong nuclear force, atomic nuclei would fly apart, as there would be nothing to counteract the repulsive electromagnetic force between protons. The universe would be composed of nothing but isolated protons and neutrons, with no stable elements or compounds. If the weak nuclear force were eliminated, stars would be unable to produce energy through nuclear fusion. The fusion reactions that power stars and create heavy elements would cease, leaving the universe cold and lifeless. The weak force is also responsible for certain types of radioactive decay, which play a key role in the evolution of matter over time. This thought experiment highlights the essential role that each of the fundamental forces plays in the structure and evolution of the universe. The hidden code of existence is not just a set of isolated rules. It is an intricate web of interactions that allows the universe to exist in its current form. The fundamental forces of nature are the building blocks of the universe's hidden code, shaping everything from the behavior of particles to the formation of galaxies. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force each operate according to precise rules, and their interactions create the complex and dynamic cosmos we observe today. As we continue to explore the universe, the quest to unify these forces under a single theoretical framework remains one of the greatest challenges in physics. Unlocking the true nature of these forces could reveal new insights into the origin and fate of the universe, helping us to decode the deepest mysteries of existence. In the next chapter, we will turn our attention to another aspect of the hidden code: the structure of space and time itself. We'll explore the nature of the space-time continuum, the role of relativity, and how the fabric of the universe may be connected to quantum processes at the smallest scales. The fabric of space and time. Decoding the space-time continuum. In the previous chapters, we've explored the fundamental forces that shape the universe and the quantum code that governs the smallest scales of reality. But to truly unlock the hidden code of the universe, we must delve deeper into the structure of space and time itself. According to Einstein's theory of relativity, space and time are not separate entities. Instead, they are intertwined into a single dynamic fabric known as the space-time continuum. This fabric warps and stretches in response to matter and energy, shaping the universe on both large and small scales. In this chapter, we will decode the nature of space and time, uncovering how they interact with matter, energy, and the fundamental forces of the universe. We'll explore the mind-bending concepts of relativity, space-time curvature, and the expansion of the universe. We'll also investigate how space and time behave in extreme environments, such as near black holes and at the beginning of the universe. Finally, we'll dive into the search for a deeper understanding of space-time through quantum theories of gravity. The first step in decoding the hidden code of space and time is understanding Einstein's theory of relativity, which fundamentally changed our perception of the universe. Relativity is divided into two parts: special relativity and general relativity. In special relativity, Einstein showed that the laws of physics are the same for all observers, regardless of their relative motion. This theory led to the famous equation E equals mc squared, which describes the equivalence of mass and energy. Special relativity also introduced the idea that the speed of light is constant for all observers, and that time and space are relative, meaning they can vary depending on an observer's motion. One of the most striking consequences of special relativity is time dilation, which occurs when an object moves at a significant fraction of the speed of light. According to relativity, time slows down for an object in motion relative to a stationary observer. This has been confirmed through experiments with highly precise clocks, such as those aboard high-speed spacecraft or satellites, which experience a slight but measurable difference in time compared to clocks on Earth. Special relativity also predicts length contraction, which states that objects appear shorter along the direction of their motion when moving close to the speed of light. These effects are not noticeable in our everyday experience, as they only become significant at extremely high speeds. Nevertheless, they reveal the flexible and dynamic nature of space and time. General relativity, published by Einstein in 1915, takes the ideas of special relativity a step further by introducing gravity into the equation. In general relativity, gravity is not a force transmitted through space as Newton believed, but rather the result of the curvature of space-time itself. Massive objects like planets, stars, and black holes cause space-time to bend, and this curvature affects the motion of objects and the passage of time. One of the most dramatic predictions of general relativity is the existence of gravitational time dilation, where time moves more slowly in stronger gravitational fields. For example, time passes more slowly near the surface of a planet like Earth than it does far away in space. This effect has been measured using atomic clocks and must be taken into account in technologies like GPS satellites, which orbit Earth and experience slightly less gravitational time dilation than clocks on the ground. In Einstein's theory of general relativity, gravity is the result of the curvature of space-time. Massive objects, such as stars and planets, bend the fabric of space-time around them, and this curvature causes objects to move along curved paths. This idea can be visualized by imagining space-time as a rubber sheet. When a heavy object is placed on the sheet, it creates a dent or depression, and smaller objects placed near it will roll toward the center of the dent, simulating the effect of gravity. The degree of curvature in space-time depends on the mass and energy of the object causing it. For example, the Earth causes a relatively small curvature in the space-time around it, which is why objects like satellites orbit the planet. The Sun, being much more massive, causes a greater curvature, affecting the orbits of planets in the solar system. In regions of space where gravity is extremely strong, such as near black holes, the curvature of space-time becomes so extreme that even light cannot escape. This is what creates the event horizon of a black hole, the point of no return, beyond which nothing can escape the gravitational pull of the black hole. One of the key predictions of general relativity is that the presence of mass and energy can cause gravitational waves, ripples in the fabric of space-time that travel at the speed of light. These waves are produced by cataclysmic events, such as the merging of black holes or neutron stars, and were first directly detected by the LIGO Observatory in 2015. The discovery of gravitational waves has opened up a new way of observing the universe, allowing us to detect events that were previously invisible to traditional telescopes. In addition to the curvature of space-time caused by gravity, another fundamental aspect of the universe's structure is its continuous expansion. This discovery, first made by Edwin Hubble in the 1920s, revealed that galaxies are moving away from each other, and the farther away a galaxy is, the faster it appears to be receding. This phenomenon is described by Hubble's law and is evidence that the universe itself is expanding over time. The expansion of the universe is not due to galaxies moving through space, but rather the expansion of space itself. Imagine the universe as a balloon being inflated, with galaxies represented by dots on the surface of the balloon. As the balloon expands, the dots move farther apart, even though they are not moving themselves. It is the space between them that is growing. This expansion is described by the cosmological principle, which states that the universe is homogeneous and isotropic on large scales, meaning it looks roughly the same in all directions and locations. However, the discovery of the expansion of space raised profound questions about the origin and fate of the universe. The expansion of the universe is currently accelerating, driven by a mysterious force known as dark energy. Dark energy makes up roughly 70% of the universe's total energy density and is responsible for the accelerated stretching of space-time. Its nature remains one of the greatest mysteries in cosmology, but its effects are undeniable. As space continues to expand, galaxies are moving farther apart at an ever-increasing rate. If this expansion continues indefinitely, the universe may eventually reach a state known as the Big Freeze, where galaxies drift so far apart that they become isolated, stars burn out, and the universe becomes a cold, dark, and empty place. Alternatively, if dark energy were to reverse or weaken, the expansion might slow down and eventually reverse, leading to a big crunch where the universe collapses back into a hot, dense state similar to its origin in the Big Bang. Black holes are among the most extreme objects in the universe, where space and time are warped to their limits. A black hole forms when a massive star collapses under its own gravity, compressing its mass into an incredibly small volume. The result is a region of space where the curvature of space-time becomes so extreme that nothing, not even light, can escape. At the center of a black hole lies the singularity, a point where space-time curvature becomes infinite and the known laws of physics break down. The singularity represents a region where general relativity and quantum mechanics collide, making it one of the greatest challenges in theoretical physics to understand what happens inside a black hole. Surrounding the singularity is the event horizon, the boundary beyond which nothing can escape the gravitational pull of the black hole. Time itself slows down near the event horizon due to the intense gravitational field, a phenomenon known as gravitational time dilation. An outside observer would see an object falling into a black hole appear to slow down and freeze at the event horizon, though the object itself would experience a rapid and extreme descent into the singularity. Black holes also offer a unique window into the unification of quantum mechanics and gravity, as they represent regions where both quantum effects and the warping of space-time are crucial to understanding their behavior. The study of black holes may one day provide key insights into the nature of quantum gravity and the hidden code that governs the fabric of space and time. One of the most significant challenges in modern physics is the search for a theory that unifies general relativity with quantum mechanics. While general relativity describes gravity and the curvature of space-time on large scales, quantum mechanics governs the behavior of particles on the smallest scales. These two theories, despite their immense success in their respective domains, are fundamentally incompatible with each other. The search for a theory of quantum gravity aims to bridge this gap by developing a framework that explains how gravity works at the quantum level. One of the leading candidates for quantum gravity is string theory, which proposes that all particles are composed of tiny, vibrating strings of energy. In string theory, gravity emerges as a result of the interactions between these strings, and space-time itself is thought to be made up of tiny, discrete units. Another approach to quantum gravity is loop quantum gravity, which suggests that space-time is composed of discrete loops that give rise to the fabric of reality. According to this theory, space-time is not continuous, but is instead made up of tiny, indivisible units that form the structure of the universe. Quantum gravity is crucial to understanding the most extreme environments in the universe, such as the interior of black holes and the very early moments of the universe during the Big Bang. Unlocking the hidden code of quantum gravity could provide profound insights into the nature of space and time, revealing the true structure of the universe at its most fundamental level. Imagine that you have the ability to bend space-time and create a wormhole, a tunnel through the fabric of space and time that connects two distant points in the universe. By traveling through this wormhole, you could instantly move from one side of the galaxy to the other, bypassing the vast distances of space. As you approach the wormhole, you witness the extreme curvature of space-time, bending and warping around you. The tunnel itself is a region of space where the normal rules of geometry break down, allowing you to take a shortcut through the cosmos. But as you travel through the wormhole, you encounter the paradoxes and challenges of space-time. How does time behave inside the wormhole? Is it possible to travel backward in time by navigating through the curved regions of space? And what happens if the wormhole collapses while you're inside? This thought experiment highlights the strange and counterintuitive nature of space-time and the possibilities that lie within the hidden code of the universe. It reminds us that space and time are not fixed and unchanging, but are dynamic and malleable, shaped by the forces and matter within the universe. The nature of space and time is one of the most profound aspects of the universe's hidden code. From the warping of space-time by gravity to the expansion of the universe driven by dark energy, the structure of space and time shapes the behavior of matter, energy, and the fundamental forces. As we continue to explore the universe, the search for a unified theory of quantum gravity may unlock new insights into the fabric of reality, revealing the true nature of space-time at both the smallest and largest scales. In the next chapter, we will turn our attention to the cosmic frontier, exploring the mysteries of dark matter and dark energy and their roles in the hidden code of the universe. The dark universe. Unlocking the mysteries of dark matter and dark energy. As we've explored the fabric of space and time and the forces that govern the universe, we've uncovered many layers of the hidden code that shapes existence. But our understanding of the universe is far from complete. In fact, everything we see, all the stars, galaxies, planets, and even ourselves, makes up only a small fraction of the total content of the universe. Most of the universe is made up of dark matter and dark energy, two mysterious components that we cannot see or directly detect, yet their effects are undeniable. In this chapter, we will delve into the dark universe, exploring the nature of dark matter and dark energy and how they interact with the visible universe. We'll investigate the clues that have led scientists to infer their existence, the experiments that aim to uncover their properties, and the role they play in the structure and fate of the cosmos. Understanding these unseen forces is key to decoding the full hidden code of the universe. Let's begin by examining dark matter, which accounts for about 27% of the universe's total mass and energy. Dark matter is called dark because it does not emit, absorb, or reflect light, making it invisible to telescopes. However, its gravitational effects on galaxies and galaxy clusters reveal that it is there, shaping the large-scale structure of the universe. The first hints of dark matter came in the 1930s, when astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving too quickly to be held together by the visible mass alone. He concluded that there must be an unseen mass providing the necessary gravitational pull to keep the galaxies bound within the cluster. This was one of the earliest pieces of evidence for dark matter, though it wouldn't be widely accepted for decades. Later, in the 1970s, astronomer Vera Rubin made a breakthrough observation that provided even stronger evidence for dark matter. She studied the rotation curves of galaxies and found that the outer regions of galaxies were rotating much faster than expected, given the amount of visible matter. According to Newtonian physics, the stars at the edges of galaxies should move more slowly than those near the center, but Rubin's data showed that they were moving at nearly constant speeds. This implied that there was a large amount of invisible mass, or dark matter, surrounding galaxies, providing the extra gravitational force needed to account for the observed rotation speeds. The nature of dark matter remains one of the most significant mysteries in cosmology. It does not interact with ordinary matter through the electromagnetic force, meaning it doesn't emit light, interact with atoms, or participate in chemical reactions. Instead, dark matter only interacts with other matter through gravity and possibly through the weak nuclear force. This makes it extremely difficult to detect directly. Scientists have proposed several candidates for dark matter particles, including weakly interacting massive particles, WIMPs, and axions. WIMPs are hypothetical particles that would interact with normal matter through the weak nuclear force, while axions are extremely light particles that could interact with photons under certain conditions. Despite extensive searches using underground detectors and particle accelerators like the Large Hadron Collider, LHC, no direct evidence of dark matter particles has been found so far. However, dark matter's gravitational effects are crucial for understanding the formation and evolution of galaxies. Without dark matter, galaxies may not have been able to form at all. Dark matter acts as a kind of cosmic scaffolding, providing the gravitational glue that holds galaxies together and allows them to grow and merge over billions of years. Simulations of galaxy formation show that dark matter forms a web-like structure throughout the universe, known as the cosmic web, where visible galaxies form along the densest regions of dark matter. While dark matter accounts for a significant portion of the universe, an even more mysterious component is dark energy, which makes up roughly 70% of the universe's total energy density. Dark energy is believed to be responsible for the accelerating expansion of the universe, a discovery that shook the foundations of cosmology in the late 1990s. Before the discovery of dark energy, most scientists believed that the expansion of the universe, which began with the Big Bang, was gradually slowing down due to the gravitational pull of matter. However, observations of distant supernovae by two independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, revealed that the expansion of the universe was not slowing down, but speeding up. This was a shocking and unexpected finding, and it implied the existence of a new repulsive force that was driving the accelerated expansion. Dark energy is often described as a form of vacuum energy or cosmological constant, a term originally introduced by Einstein in his equations of general relativity. Einstein had added the cosmological constant to his equations to balance the attractive force of gravity and keep the universe in a static state. However, when the expansion of the universe was discovered in the 1920s, Einstein abandoned the idea, calling it his biggest blunder. Ironically, the discovery of dark energy suggests that Einstein's cosmological constant might not have been a mistake after all, but rather a crucial component of the universe's hidden code. The nature of dark energy is still unknown, but it has profound implications for the fate of the universe. As the universe continues to expand at an accelerating rate, galaxies are moving farther apart, and over time, they will drift beyond the reach of our telescopes, disappearing from view. If dark energy continues to dominate, the universe could eventually experience a big freeze, where all stars burn out, galaxies become isolated, and the universe becomes cold and dark. Another possibility is the Big Rip, a scenario in which dark energy's repulsive force grows stronger over time, eventually tearing apart galaxies, stars, planets, and even atoms. In this extreme scenario, space-time itself would be stretched to the breaking point, leading to the ultimate destruction of the universe. Some cosmologists have proposed alternative explanations for dark energy, such as quintessence, a dynamic form of dark energy that evolves over time. In this model, dark energy could either weaken or strengthen as the universe ages, leading to different possible outcomes for the future of the cosmos. One of the most striking features of the universe is its large-scale structure, often described as a cosmic web. This web-like pattern is formed by the distribution of galaxies and dark matter, creating a vast network of filaments, walls, and voids that stretch across the universe. The cosmic web is not a random arrangement of galaxies, but a highly structured system that has been shaped by the interplay of gravity, dark matter, and dark energy. The filaments of the cosmic web are regions where dark matter is most concentrated, and they act as the bones of the universe, guiding the formation of galaxies and galaxy clusters. Between these filaments are enormous voids, where matter is scarce and galaxies are few and far between. The cosmic web extends over hundreds of millions of light years and is one of the most striking examples of the hidden code of the universe. Mapping the cosmic web has provided astronomers with critical insights into the distribution of dark matter and the role of dark energy in shaping the universe. By studying the large-scale structure of the cosmos, scientists can test different models of dark energy and gain a better understanding of how the universe's expansion has evolved over time. One of the key tools for mapping the cosmic web is the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB provides a snapshot of the universe as it appeared just a few 100,000 years after the Big Bang, before stars and galaxies had formed. Tiny fluctuations in the temperature of the CMB reveal the seeds of the cosmic web, where regions of higher density would later collapse to form galaxies and clusters of galaxies. Despite the overwhelming evidence for the existence of dark matter and dark energy, their true nature remains one of the greatest unsolved mysteries in science. To unlock the hidden code of the universe, scientists are conducting a variety of experiments to detect dark matter and understand dark energy. For dark matter, several experiments are underway to try to detect WIMPs or other dark matter candidates. These experiments typically take place deep underground to shield them from cosmic rays and other sources of interference. One of the most famous dark matter experiments is the Large Underground Xenon, LUX, detector, which searches for the faint interactions between dark matter particles and normal matter. Other experiments, like CERN's Large Hadron Collider, LHC, attempt to create dark matter particles in high-energy collisions between protons. For dark energy, the challenge is even greater, as its effects are only noticeable on the largest cosmic scales. Astronomers are using large-scale surveys, such as the Dark Energy Survey, DES, and the Euclid mission, to map the distribution of galaxies and measure the expansion rate of the universe over time. These surveys aim to uncover more about the behavior of dark energy and whether it remains constant or evolves over time. Unlocking the mysteries of dark matter and dark energy is crucial to understanding the full hidden code of the universe. These invisible forces shape the cosmos in ways that we are only beginning to comprehend, and discovering their true nature could revolutionize our understanding of physics and the universe's fate. Imagine that dark matter and dark energy did not exist. What kind of universe would we live in? Without dark matter, the universe would look very different. Galaxies, if they existed at all, would be much smaller and less stable. The gravitational pull of visible matter alone would not be enough to hold galaxies together, and many galaxies would have dispersed into loose collections of stars. The cosmic web, the grand structure of the universe, would not have formed, leaving a universe with little large-scale structure. Without dark energy, the universe would still be expanding, but the expansion would gradually slow down. Gravity would eventually halt the expansion, leading to a big crunch, where the universe collapses back into a hot, dense state, possibly leading to another Big Bang. The accelerating expansion that we observe today would never have occurred, and the universe would have a very different fate. This thought experiment highlights the critical role that dark matter and dark energy play in shaping the universe. Though they are invisible and mysterious, they are essential components of the hidden code that governs the cosmos. Dark matter and dark energy are two of the most enigmatic components of the universe, yet they hold the key to understanding its structure and fate. Together, they make up 95% of the universe, leaving only a small fraction composed of the ordinary matter we can see and touch. As scientists continue to explore the dark universe, they are uncovering new layers of the hidden code that governs existence. While the true nature of dark matter and dark energy remains elusive, their effects are undeniable, and unlocking their secrets could lead to revolutionary discoveries in physics, cosmology, and our understanding of reality.